So I like today because I like alternate light sources and I like fluorescent stuff. And the only downside is all of my UV lights are still coming back from Cleveland, so they're in the post. So I couldn't bring them and we couldn't do the fluorescent stuff. But anyway, today we're talking about alternate light sources. And so the number one goal for changing your light source is to find hidden evidence or evidence that's hard to find. And we'll see some examples of that today. Of course, we have the analytical methods for large samples, extraction, isolation, characterization, but a lot of times we have a hard time finding those samples. We also could do colorimetric comparisons, so forensic colorimetry or forensic photography that we talked about last time, looking at color to enhance contrast. We could use color filters to block out certain colors and try to find evidence that was masked by color. But today we're going to be using spectral characterizations and changing this light source and changing the detector a little bit. So in terms of paint and so on, we're getting even more into using microscopic methods too. So FTIR and Raman spectra collected through a microscope. And then we have these ASTM standards on ink analysis and paint analysis. And in these standards, you have flowcharts for how to decide what technique to use for the different parts of the evidence. So let's look at one of those flowcharts. So here's an ASTM analysis flowchart. And up at the top, you can do the physical examination. You could look at layers, like if you have a paint chip, is it multi-layer, like from an automobile? Like we saw last time, there were, sometimes up to 5 different layers. And so you would characterize the physical properties, and then you would get into trying to figure out the chemical properties of those layers. Okay, so for the organic components, we get into fluorescence microscopy, and then we can also use alternate light sources to look at the dyes and also looking for fluorescence there, and then in the microscope. So using fluorescence in the microscope, but today we're going to be focused on using fluorescence to discover fluorescing soils in the crime scene. So we'll be looking at finding hidden evidence. Now you have inorganic components too, metals and heavy elements in these different formulations. And so you'd use something like a scanning electron microscope to find the particles, and then using the X-ray fluorescence that comes out of that. So if you focus the electron beam on the heavy elements, you'll knock out core electrons, and then you'll get characteristic X-rays. And it'll essentially tell you what elements you're dealing with. Now, they have to be heavy elements because really the second row, in particular carbon and oxygen and nitrogen, they're on everything. So we're just in a carbon-based biosphere, and so you're not going to get really any forensically relevant information from the second row. So it's third row and beyond is what you're going to get. So that's why I say heavy elements, not just metals, but you might get chlorides, bromides, things like that, some of the non-metals. And then we get down here to microspectrophotometry. So this is a long word, but it's spectroscopy through the microscope. You can do UV vis through a microscope, FTIR, and Raman. So you can do all of those different spectroscopic techniques through the objective of a microscope. Now, some of those are a little more difficult. So in the infrared, the lenses that you would have to use would have to be made out of salt. Well, that's really difficult, especially here in Huntsville where it's super humid. And so in order to not have to use potassium bromide optics, because they would fog in this humid atmosphere, they use mirrors. And so similar kind of mirrors that you would use for a telescope to collect faint light and bring it to an objective, they just miniaturize all of that and use mirrored objectives for the infrared microscope. So we have one of those in my research lab. You've probably seen it when you come up there to do CHEM work. But the objectives are kind of big and bulky. It's because they're made out of mirrors. And this, and so it's micro for the microscope, spectro for the spectroscopy part, and then photometry is really, it's the measurement of photons. So you're counting photons. You're not necessarily, you're using that detector to count the strength of the signal. So it's microspectrophotometry. Now, like I said at the beginning, the main goal for using an alternate light source is to find hidden evidence. And so here's some examples of obliterated writing. So up above, if you take a visible photograph of this document or this sheet or whatever this is written on, and it's been obliterated, say with a Sharpie. If you change put a filter on the camera to block out the visible light and look in the near infrared, which is just right next to the red spectrum. So you have the near infrared and then the mid infrared and then the far infrared. So those decrease in energy. So you have the visible light, which is more energetic than the infrared light. So right next to the visible spectrum is what we call the NIR, the near infrared. So that's, in the 800, 900, 1,000 nanometers. Okay. Then you get out to the mid-infrared. That's where you have the regular FTIR spectrum that we're used to seeing with the fingerprint region, the CH stretches, and so on. So the visible spectrum is around 15 to 20,000 wave numbers, and 4,000 wave numbers is the maximum on the mid-infrared. So between 4,000 wave numbers and 15,000, that would be the near infrared. And so here you can see sort of through the ink that's been obliterated, and this will work best when, say, this was written with a different kind of ink, a different kind of pen. So if this was like a ballpoint pen and then they obliterated it with a Sharpie, those have different spectral signatures. So you might be able to see through one ink and reveal the other. Okay. So if you're going to obliterate writing, use the exact same pen and the exact same ink. But is anything ever the same? So if oxygen has had time to interact with this ink and maybe age it a little bit, there may be a spectral difference even if the same pen was used. So it'd be old and fresh ink. So there's a possibility that it could still be revealed. So don't obliterate things, or just don't do bad things. Okay, so with the alternate light source, what we're doing is we're changing the illumination source. So this is most of today's lecture is talking about alternate light sources. And so we'll get into what's going on here. These different visible sources of light, we've talked about this in the last lecture. You've got sunlight here. So you've got the super hot sun, really bright. You've got wavelengths of light. So if this is that black body radiator, a good match for the solar spectral light, at least as it's viewed through our atmosphere, would be 6,500 Kelvin. The tungsten lamp has a hard time getting up to that temperature, so you might say 4,000 Kelvin, or maybe even as low as 3,000. And that gives you that red, or not really red, but kind of yellow light that you get from a tungsten lamp. Now, a white LED has 3 phosphors in it. So it's got a red, green, and a blue phosphor, and you can kind of see their spectral profiles here. So that green is really the overall signature from the 3 lights that are in a white LED. The mercury vapor lamp, we had a good spectrum of that when we did the CHEM lab, the RGB CHEM lab. We could shine that spectrometer up at the mercury vapor lamps that we have here. The fluorescent tube lights that we have in this room have mercury as their light emitting source. You also saw that with the Cheez-It spectrometer. Didn't I bring that? Did I bring that to this class? You look around, you can see the red, green, and blue light coming out of these fluorescent lights. If you're at HEB and you're scanning your groceries, that's going to be an LED laser. They used to be helium neon, but I think now they're just LED. But look how narrow this is. So this is the thing I want to point out too. Laser light sources and LED sources, we'll see later, have a very narrow spectral envelope. So this is a band of frequencies or wavelengths here. And so the laser lights, they call them spectrally bright. So they have very narrow bandwidth, very narrow band of light, and very bright, and a lot of photons coming out at a very narrow range of wavelengths. We use that to our advantage. So there's different forensic light sources that you can buy. You can get a quartz halogen lamp. Now that's a tungsten, or the quartz is actually the container. the filament is actually made out of tungsten, and it has a halogen around the outside of it to raise the temperature of the tungsten, so you get more visible light out of it. But it really doesn't get much into the UV, and it's super hot. So it runs very hot, and it's not a great fluorescence light source because it has limited UV light. Then you have metal halides. It gives a limited UV, but very bright peaks requiring expensive filters. So because both of these generate so much heat, the filters are expensive because they have to be able to handle that heat. You want to block the light that you don't want to use in searching for the evidence. Xenon lamps, they're good, and they have a flat response in the visible region. We'll see a spectrum from a xenon lamp in a minute, but it also runs very hot. More light is coming out in the infrared from these sources than in the visible or in the UV. So in all of these ones that generate enormous amounts of heat, your filters have to be made out of high quality glass, and they're more expensive. For an LED, you could get by with a pretty inexpensive filter if you need one at all. So LEDs have an advantage because they're wavelength specific. They have that narrow band of wavelengths, and they're, all of the energy is going into producing those photons in that narrow band. So they don't generate very much heat at all. And they have a long life. Okay. Part of the reason they have a long life is there's no filament that heats up and cools down. So if you think about a paper clip, you bend it a few times and it'll break. That sort of stress, it gets brittle with stress. The tungsten filament, when it heats up, it expands. When it cools down, it shrinks. And so over time, that's going to get more and more weak, and it's going to break. Okay. We don't have anything like that in the LED light. So here's the xenon arc lamp. It's a little bit different picture than what you have in your notes if you downloaded your notes before yesterday afternoon. But you can see that if you were to integrate the area under this spectral curve, most of the photons are in the infrared. And we're not going to be able to use those, except for the near infrared cameras, maybe. Most of those are passive. You don't need a light source. We've got plenty of infrared in the room. So if you put a near infrared filter on your camera, blocks out all the visible light, and you're going to be able to see in the near infrared, and you'll be able to see this enhanced contrast if you have something that's got a different temperature to it. If you get into the visible, that's where we would use the filters. We might bring in the UV light and look in the red shifted light for fluorescent samples. But you can see there's UV light available in this light source, but it's only this amount. What percentage of that is of this whole integrated emission? What percentage of that is UV? It's pretty small. Now there's a lot of forensic light source manufacturers, and this is also where you can buy your camera filters and so on. So we'll look at some of their products. So light sources allow us to find and visualize more evidence. So that's really what we're doing. We can do forensic photography in the visible region, but maybe there's something on a carpet, on a bedspread, or whatever, and it's just lost in the busyness of the pattern, okay, or the fibers themselves. And so we're looking for evidence that may be obscured by the environment. And so in order to work efficiently, we need to know how to utilize spectroscopy to our advantage. And one of the best pieces or tools is fluorescence. Now, light can be used for all these different kinds of methods. We can find gunshot residue. We can find latent prints. They make fluorescent fingerprint powder that you can put on prints. We can find fluorescent fibers. We can use grazing angles. So just a regular flashlight grazing across the surface, the particles will bounce the light up into your eye or into your camera. But if there's no particle there, the light will graze off the surface and not go into the camera. So you won't see very much light at all, but wherever there's a fiber or a particle on the surface, if the light's coming in at a grazing angle, then you'll see light hitting your detector, your eye or your camera. And so we can operate these detectors, cameras, in absorption mode or specific illumination mode. So we're trying to enhance contrast against a colored background. So we can change the incident of angle of the light source, just like I was saying, grazing angle illumination is good for detecting particles and fibers. And then we can use fluorescence mode. So since fluorescence mode is a little more tricky, that's what we're going to spend most of our time talking about. Back to near infrared imaging. You can buy cameras now that are full spectrum, but in the past we had to take the camera apart and remove the filter that filtered out the UV or the near infrared light. So they put filters in the camera sensing elements to just focus on the visible range. Why would you do that? You would think you'd want a camera that was sensitive to everything, but when you narrow the number of photons hitting your detector, you're also narrowing the noise. And so by filtering it down, you let the camera turn up its sensitivity and not be, it will be able to detect the photons without having to turn up its sensitivity. So that keeps the noise level down. And I thought this was a really great image that I found online of obliterated writing. So here, you can't tell that there's an image here at all, although maybe you can kind of see, since you know there's a turtle there, you might be able to pick it out, but it's been obliterated. And just changing the camera sensitivity range, you're able to see through this whatever ink they use, felt marker or Sharpie, and you can see that cute little turtle. I saw that, I was like, oh, I love that turtle. Here's some different paints, and now you can buy some of these cameras right off the shelf, a full spectrum camera. Here's the Fujifilm FinePix camera, which can see in the near infrared. So if you put a visible filter on this camera, you're blocking out the visible, and then the camera is more sensitive in the near infrared, and you can see through those paints. So you can reveal the writing behind the different paints. Also, it can see through like charring. So here's a charred sample. And so you can see some of the text where it's not charred, but right here you don't see it in the visible range. If you take a picture of that object in the near infrared, you can see the writing a little bit more. It's still charred down here, but you can see a little bit more of the writing, and you can reveal the writing even though this sample's been charred. Let's talk about contrast enhancement. You can use the opposite color to eliminate a particular color. So blue light will eliminate reds, and so you can use different colored filters on your camera. And so you use red viewing filters will enhance the reds, and blue light will eliminate those reds. So let's get to the fluorescence now. So this is my favorite part because I'm a spectroscopist. You have two parts to fluorescence spectroscopy, but also fluorescence photography. You have the excitation beam or excitation light, and you have the emission light. And your sample converts one to the other. So this piece right here is being done by the evidence that you're looking for. And so you remember this from PCHEM 1, you have the ground state, ground electronic state. And to review, this is visible and UV, so this is dealing with the electronic cloud of the molecules. We're not doing anything with the vibrations, although there's vibrations involved, but we're really focusing on the electron cloud. It's absorbing light. And so you hit that with the excitation beam, the blue beam here, and you excite that molecule up here to an excited state. And sometimes there's a conversion. In a fluorescence sample, there'll be some sort of relaxation. So this vibrational relaxation, and we might even get a shift over to another potential energy surface. And this would be the emission excited state. Goodness gracious, can't write. And look at what happened. When we talk about relaxation, we're going down in energy. Does that make sense? When you relax the system, you're dropping in energy. So if we drop in energy, the emission arrow has to be shorter than the excitation arrow. Everybody remember that. So excitation is the longest arrow. That means it's the shortest wavelength. Then we have some relaxation. We drop in energy, and then the emission arrow is, by definition, it has to be shorter than the excitation arrow. So when it's a shorter arrow, that's a longer wavelength. So that's the important part and why we can use this in forensics evidence search. So this is the fluorescence emission, and you see that arrow is shorter, so this is red shifted. And so this is a good setup. We can have a light source. Let's say we had that xenon lamp. And on that lamp, we don't want to illuminate everything, all the wavelengths. We just want to illuminate with the blue light. And so we'll put a blue filter on that excitation lamp and we can shine it around. And then our goggles and our camera will have a filter that blocks out the source light. So if we have no fluorescent substances in our field of view, it's going to be black. We'll turn out the room lights. We'll have our blue source. We're shining blue light everywhere, but we've got orange glasses on and we don't see anything. But then we find a fluorescent stain or something, like, okay, here's some evidence. That might be a bodily fluid. And so we're looking with the red light, we're blocking out the excitation light. We won't see anything except fluorescent compounds, because the fluorescent substance will convert this excitation light and it will emit over here. And when it emits over there, then our camera and our eye can pick it up. So here's some bodily fluids. Here's a crime scope. Notice it's got matching goggles and camera filters. And so what you see with your eye, you say, okay, there's something there. Then you can use that filter on your camera and you can capture that. And you can see how bright it is in many cases. So this is the setup. In order to isolate the fluorescence light, we have a blue filter on the source. And so we use that emission filter to select the illumination wavelengths. And we use a detection filter to block those illumination wavelengths. And only fluorescence wavelengths will be detected. So let's talk about the filters. They come in two flavors, and there's pretty big difference in cost. So interference filters are more complicated and more expensive in general. And they will tolerate more heat than an absorption filter, but they're also focused on a very narrow range. And so if you had a laser illuminator, say you had a 785 nanometer laser, a ND YAG laser that was green, and you're shining that around, you could put an interference filter on your detector that would just block that green light. And so anything that happened to that emission light, whether it went blue or red, you would be able to detect, because we're just blocking the green light. Okay, this is how an interference filter works. So the light, if you follow the blue wavelength coming in, it comes in, enters the filter, and you've got a specific coating on here that that blocks that wavelength of light efficiently. It reflects it, and so then the blue light reflects back as the red light here, and then it comes back here and reflects again as this yellow color. And then when it comes back here, notice it's completely out of phase with the blue light. Now, blue and red in this case, I'm not talking about that in terms of its spectral position, blue and red. I'm just saying try to keep track of the two reflections we have here. So the first one comes in, hits here, bounces back, comes back, and then it's this greenish yellow. And when they come back to the front, they're out of phase with each other. And so they have destructive interference. So that's how an interference filter works. It's kind of like you manage the thickness of this glass or this film so that it's a number of wavelengths plus a half, so that it'll always be out of phase when it's going through this. Now, where does the energy go? The conservation of energy says that we cannot create or destroy energy. We can only convert it. And what this is doing is it might have a destructive interference when you're coming straight onto this filter at a 90-degree angle, right? But if you're coming at a slightly different angle, you'll get constructive interference, where these waves will be in phase with each other, and you'll get more light out at certain angles, where you get a bright rings coming around. Let's say you shoot a laser through an interference filter, you won't get any green light coming straight through, but then you'll have bright green rings out here, and it's just a resonant cavity. So we're not losing energy, we're not destroying energy, we're just redirecting it. And so straight on, you won't have light coming out. Now, absorption filters, you just put any thickness of glass or whatever you put an absorptive material in there. You can make these wavelength specific. You can put things that absorb red or green or blue. Or you can have a neutral density filter, which has different amounts of carbon black in there that absorb all the wavelengths. And it just reduces the total amount of light that comes through. And this is that absorption curve, Beer's law. It drops off, at exponential amounts. And so the thickness or the amount of absorptive material you put in that filter, the steeper this red curve is, and the less light that comes through. But now this is absorbing, so it heats up. So if you have a really, really bright light source, like those xenon arc lamps and so on, they're putting out an enormous number of photons. And if you're just trying to filter out just a little narrow band of UV light or blue light, you're having to absorb all of those other wavelengths. And so you need a cooling fan, you need to keep the light and the absorptive filters cool. And so let's talk about these different kinds of filters. This is a long pass absorption filter. So what's on the y-axis is transmission, and up at the top you have 100% transmission. And so this spectral line over here is showing that there's no transmission here, so it's blocked. And up here it's transmitted. So you look at these curves, just always double check the y-axis to make sure it's transmission. If it's transmission, then when the line goes up to the top, then you've got an open window there. And so this passes, in this case, some red light and all this infrared light. So this is the near infrared region. And it's going to have an edge wavelength. So we find where this window opens up. You could pick the 50% mark if you want and come down. And so this is going to be around a 750 nanometer edge wavelength. Do y'all see that? So it's where that steep part is. So this is a long pass filter. What's the word long referring to? This is the interactive part. Yeah, long wavelength. Now this is sometimes called a low pass filter. So someone else, tell me why it would be a low pass filter. What's the low referring to? Wave number, and that's proportional to energy. So low energy, it's passing the low energy photons. Okay, so long wavelengths and low energy are the same thing. So it's low pass for low energy passing, and it's a long pass for long wavelength passing. Those are the same thing. So that's synonymous. Okay, here's short pass absorption filters, a whole bunch of them. And I've got the edge wavelengths labeled here and somewhat sort of an estimate of their colors, although the 250 is no good because that's UV. It's orange. That's so ignore the colors. But you can see the different edge wavelengths. So here's one that, you know, it breaks 50% at 400. This one's 385. This one's 350, and so on. Now these are also called high pass filters. Can you figure that one out? Yeah, so short wavelength is high energy. Now these last few right here, these might be passing a little bit of blue, and but most of these are UV. So this is the UV range here. So these would be fantastic filters for doing fluorescence because you put UV light into the molecules, and if they have, most molecules will absorb UV light. If they've got any double bonds or anything like that, then they're candidates for fluorescence. So at least they get a good absorption in the UV. If there's any fluorescent molecules in the region, then they'll convert that over to visible light, and you'll see visible light coming. Then the last type of filter we have is a band pass filter. And these all three that we've just covered are absorptive filters. So they're absorbing. So this is transmittance here. So in this low region down here, they're absorbing. They're blocking that light by absorption. So these are absorptive filters. So this is a band pass absorption filter. So this isn't about musical instruments. What is it talking about? It's talking about a band of wavelengths. And so it's this band of wavelengths that's being passed. And so if we need to know something about this, we have two edge wavelengths, and so that gets kind of cumbersome, but so they'll just label it as the central wavelength. So this one, we pick that 50% mark, put a dot in the middle, and try to estimate what that central wavelength would be. So that might be 705. Okay, and it might be, plus or minus 45 if you want to say that. So this one's got a band pass of 90 nanometers centered on 705. And so if you got a box, you open it up, that's the information that would be listed for that particular filter. What about this green one here? Pick the 50% mark, come down here. That looks like it's halfway between 800 and 850. So that'd be 825. Plus or minus, what do we have? Let's say 30. Would you say 30? And then here, this red one's a little bit more narrow. So it's coming in at, what, 940? And I don't know, what are your estimates? 20? Plus or minus 20? Close enough? Okay. And so you can see this is a much narrow band, plus or minus 20 nanometers versus plus or minus 45. Now the really narrow one might even be called a notch filter because it's just like a notch in the spectrum. That's all that's passing. Okay. Here's the xenon scope. You can see it's kind of bulky. This one pulls quite a bit of power. You've got some nice things here. This, where he's got his thumb on, this is a built-in filter enclosure. But the reason it's so bulky is because it generates heat, so a cooling fan. So it's not too bulky, but I mean, it is bulkier than an LED flashlight. Okay. So here's the hand scope specifications. It does have 12 volts. It can run on a battery, but it's going to use quite a bit of power. It's got 7 filters inside, so there's 2 positions. Actually, it looks like 2 7 positions, so they can do 14 filters. Set of different goggles that you get, and then 4 camera filters, 2 red and 2 orange. Then you have the LED lights. So these are crime lights that you can get that are focused on particular areas. So here's sort of a selection guide for all the different LED flashlights that you can get. And so you don't need filters for these on the source. So if you buy this 385 or 365, that's how narrow that LED light source is. So you don't need filters on your light source. You're not throwing away any other light. So when we talk about efficient light sources, LEDs are the best because you don't have to filter anything out. The downside is if you want to try a UV light or a blue or an orange, you got to have different flashlights. So you got to buy a whole kit. Whereas the previous one, the xenon scope, you have one light source with a bunch of filters. So I don't know. It's up to you which one you think is best, but you get more light in this narrow region than you would get out of that little hand scope. And so the other advantages of LEDs, there's no mercury or toxic gases. There's no fragile filament that breaks, that expands and contracts when it heats up and cools down. Some of these high voltage, like the metal halides, they have to have high voltage, and that can generate ozone, and so that's a environmental hazard. It's not good to breathe. Also, there's no infrared light or heat in the light beam, and no warm up period. And then we get into forensic lasers. These are even brighter than the LEDs because the light emitting substance is inside a resonant cavity, and it really builds up a lot of photons. Now these can be even more bulky than that handheld light, and so what they do is they'll use a fiber optic. They'll have this thing plugged into the wall, and then you got that reel with a fiber optic, and you can run around with the emitting part and set the laser in the corner. So that's pretty nice, and you can put out a whole lot more photons of light. So this 532, this would be a neodymium YAG laser. And they put some filters on the end so that it doesn't produce speckled illumination. So let's do a Kahoot and to kind of emphasize the main points.